discussed quite extensively the basic Monte Carlo, so now let's try to improve with the multilevel Monte Carlo. So I guess you, I have anticipated, and I guess you already. So the idea of multilevel Monte Carlo is to exploit multiple discretization to try to improve the complexity of this uncertainty quantification analysis. So let's introduce a sequence of discretizations. So here I consider uniform refinements, but of course you can also go beyond that. I will not discuss in this course. You could imagine to, so if you have some special features, like you work on an L-shaped domain, you can imagine to locally refine the grid around some critical points and build a sequence of locally refined meshes. You can even go further and think of refining the mesh for each realization up to a certain tolerance, so now the level becomes the sort of error that you accept from each sequence. For this lecture, I will stick to a uniform refinement of uniform sequence of meshes. So I denote L, the level of refinement, the L, up to a maximum level capital L. And each level of refinement has a corresponding mesh size, H0, H1, each capital L. And then the last level is the one we are happy with. So let's say where the bias of this Monte Carlo estimator is small enough, so it meets the target tolerance. So ideally, we would like to run our Monte Carlo analysis on this mesh here. But we want to exploit the coarser meshes to reduce the cost. And the trick or the idea is very simple. So if this is our target quantity, again, this is still not the exact quantity, so there will be a bias here, but let's say this is what we can afford. So the idea is to write this expected value of QL as a telescopic sum. So as the expected value of Q evaluated on a very coarse mesh, plus a correcting term, so the expected value of Q1 minus Q0. So we compute the same problem on two consecutive meshes and we take the difference. And then we keep on adding corrections until the last one, which is the difference between Q capital L and Q capital L minus 1. Okay, so that's just an identity. But once we have written there, then the idea is to use Monte Carlo estimators independently on each one of those terms, instead of doing Monte Carlo here. And why is this a good idea or an interesting idea? Well, because what you're doing here is that you are adding successive corrections to the initial estimate. So in these corrections, you are actually solving the same problem. By the same problem, I mean with the same realization of the underlying noise. Okay, so you draw your y random variable, whether they are coefficients or force intervals, whatever. For that random variable, you solve your problem on the level capital L and on the level capital L minus 1. And then you take the difference. Hopefully this difference is small, because you're solving the same problem on two consecutive grids. So if the grid is sufficiently fine, the difference is small. Okay? So this difference is small. It means that if I have to control the Monte Carlo error here for this difference, we know that the Monte Carlo error depends on the variance of the quantity that we are integrating. And since the variance is small, the whole Monte Carlo error is small. This means that if I want to control the Monte Carlo error on this term, hopefully a very small sample size is enough. Because I have a small variance, so I can divide by a small m, and I keep this error small. Okay? This means I need to run very few simulations on this fine grid. Okay? But if we go back here, this difference will become bigger and bigger. And in the first one, there is no difference. Actually, it's just a quantity Q0 itself, which is not small. Okay? So here I have to kill the Monte Carlo error, yes. here I have to use a big sample size, if this quantity is big, so if I want this term to be, the error in Monte Carlo to be small, I need to divide by big M. Okay? But those simulations are on a very coarse model, so hopefully the overall cost is not that much. So let's make this a bit more rigorous. So the estimator is a sum of Monte Carlo estimators for each one of those terms, so it looks like that one. So I call it mu hat MLMC, indexed by capital L, which is the maximum level of refinement that I consider. And then it will be the sum of Monte Carlo estimators for each one of those differences. Now we can write it more compactly. The sum of differences, I just introduced this notation that Q minus 1 is by definition 0. So I can write this one also as a difference, Q0 minus Q minus 1. So I can write this as a sum over the levels of Monte Carlo estimator of differences. Just keep in mind that the first is not really difference. The first is just the quantity itself, which is big. Okay? And then, again, here each one of those is a Monte Carlo estimator, which means 1 over an L, sum of these differences, evaluated for the same realization of the random variable. I use this a little bit heavy notation, where I denote this realization with a double index, YIL, to highlight that for each level, I take a certain number of realizations of the underlying random variable. But what is key is that this difference is evaluated for the same realization, because you want this difference to be small. You don't want to use independent realization in the difference, otherwise it will not be small. Okay? But then all these YIL are IID. It means they are independent within each Monte Carlo estimator, and in this version they are also independent between levels. So I do completely independent Monte Carlo realizations between the levels. One main question, the second assumption, I will come back on later, comment on this. It definitely simplifies a lot the analysis if you do independent Monte Carlo estimator for each of the differences, because then everything is somehow decoupled in the Okay, so I already explained the rationale behind this construction. So now let's try to see whether we gain eventually in something, complexity, by doing this construction here. We can use again the mean square error to quantify the accuracy of our approximation. So what is the bias of this estimator here? So if I take again the expected value of this estimator, expected value again is with respect to the whole sampling strategies, or with respect to the whole random variables that I generated. So again, here everything is linear, so it's a linear approximation. So the expected value I can pass inside the sum over the levels. So this becomes the sum over the levels of the expected value of each one of these Monte Carlo estimators. But is each one of those Monte Carlo estimators, the expected value of the estimator is just the expected value of the quantity that I'm evaluating. Okay, so I get here the expected value of QL minus QL minus 1. This is a telescopic sum. The minus 1 term is 0 by definition. So I get exactly this expected value of Q capital L. And this because of this telescopic structure, and because this Monte Carlo estimator is unbiased in evaluating the expected value of the difference itself. Okay? So what does it mean? It means that, at least in expectation, this estimator here does estimate actually the right quantity being the expected value of my output quantity on the finest grid. So in expectation, this estimator is not polluted by the fact that I'm using coarser discretization because of this telescopic property. Because those intermediate terms, they cancel exactly. So you have to be very careful if, for whatever reason you use an unbiased, a biased estimator here, you have to be very careful that you do it right. Because if the series is not telescopic anymore, then you will have a sum of terms, which might not be that small, so eventually you do pollute the final result, at least in terms of the bias. First conclusion is that the bias, so meaning the difference between the expected value of the estimator and the true quantity that I'm targeting, is the same as the Monte Carlo estimator done on the very fine grid. Okay, so the bias is the same. And so the decision on what's the finest grid I want to use is the same as in standard Monte Carlo. So what will change is the variance of the estimator. Okay, so this whole construction aims at reducing the variance of the estimator with respect to a plain Monte Carlo one. So again, the bias will be dictated only by the finest discretization, and then I can use it. I can use the same criterion and the same strategies to decide its finest level. Okay, let's look at the variance now. Again, I hope I convinced that you can do this analysis in an arbitrarily Hilbert space using this inner product structure. So if we look at the variance of the MLMC and LMC, there's a typo here, MLMC estimator, which is defined in this way. I plug in the so of course I can write mu L here. I can also, so this mu hat is a sum over the level of this Monte Carlo applied to QL minus 1. And then I have to subtract mu capital L. But mu capital L, I can also write it in this telescopic form. Okay? So also as a sum over the levels, so I can actually in each level subtract mu L minus 1. Okay? Which makes now this quantity here to have 0 mean. Okay, so I call it delta, this difference here. So now I have, I can expand this norm square using the inner product structure. So I will have a double sum over the levels of this Monte Carlo estimator applied to delta L. Inner product, the same Monte Carlo estimator applied to delta L prime. Delta being this quantity there that has 0 mean. Okay, so once again, all the cross terms drop because those are centered random variables, and you're left only with the diagonal terms, so it becomes a single sum, not a double sum anymore. We have a single sum over the levels, expected value of the norm square of this estimator, but this is exactly what we have analyzed. So this is the variance of the single Monte Carlo estimator. So you can further expand this term here, and you get the variance of this difference divided by ML. Okay, so again, by independence within the Monte Carlo and between levels, this variance analysis just gives a sum of contributions over each levels, over each realization. So this is the expression of the variance of the estimator. And of course, this variance is controlled by the sample size that I use in each level. And intuitively, since this difference becomes smaller and smaller, I can afford using a smaller and smaller sample size while keeping the whole sum under control. And that's where hopefully I will gain, because I run only few simulations on the very fine grids, which are very costly, and I run a lot of simulations on the coarse grids, which are fairly cheap. So this was the variance. We can look at the mean square error. Again, we are in the Hilbert setting, so the mean square error splits into the bias square plus the variance of the estimator. So we can just sum the two contributions. The contribution from the bias, which is just given by the discretization error on the finest level, plus this variance contribution. Okay? Good. Now, so in the Monte Carlo, we say, okay, if we want to control the error, we have to control those two terms. So the first one is controlled by choosing L, the second one is controlled by choosing the sample size, and that's fairly easy in quotes. Easy if we have an error indicator for the discretization part, and easy for the statistical part because you can estimate the sample variance and then choose M accordingly. Here is slightly more involved because we don't have to choose only one sample size, but we have to choose many. And there may be actually different choices. There are infinitely many choices that give the same overall error. Okay? So one can ask the question, is there an optimal choice? What we call an optimal allocation. If you want to define an optimal allocation, one has to define an optimality condition, an optimality criterion. And the optimality criterion is, let's try to reduce the cost, the overall cost. So let's say that we want to achieve a tolerance at tau square. We split the tolerance between the bias and the variance. So tau square over 2 is here, tau square over 2 is here. Okay, given that this whole term should be tau square over 2, is there an optimal choice of M that minimizes the overall cost? Okay. Good, so we can set this optimization problem. So let's introduce some notation. So I call VL this variance of this difference. Okay, the V0 again is not really a difference. So V0 in general is very big, but the other you hope that it becomes smaller and smaller. Similarly, I call CL the cost of generating one difference, so running two simulations on level L and level L minus 1, and C0 will be the cost of running just one simulation at level 0. Okay? So here is the optimization problem. We want so here is the optimization problem. So we want to look at all possible choices of ML for which the overall variance of the estimator, which is the sum of VL over ML, the overall variance is more or equal than tau square. Okay, here I didn't put it divided by 2, but it's irrelevant in this argument. So the overall variance is controlled by tau square, and we minimize the cost. And the cost is the sum over the levels of the number of simulations that we run on each level times the unit cost of getting that value. Okay? Of course, the minimization here is done of all non-negative, not positive integer values. So this is an integer programming. So fairly difficult to solve, but if we relax it and we accept that ML can take real values, and then we take the ceiling, the closest integer after, then the solution is fairly easy to find. It's on the next slide, and it's given by this formula here. So essentially there is an optimal allocation, and ML should be proportional to the square root of VL over CL. So variance divided by cost. Okay? Times some constant, which is given here, and should scale always by S tau to the minus 2. If you want to meet this requirement that the total variance is tau to minus 2. Okay? I could leave this. Okay, this is really very simple calculation, so you can actually write a Lagrangian for this constraint problem by adding a Lagrange multiplier. So you look for these values m0 up to m capital L, and you want to minimize the sum of MLCL, and here I put minus lambda, the constraint. That's an inequality constraint, so if the constraint is met, lambda should be positive, otherwise lambda should be 0. And then we can differentiate with respect to each ML. Okay, if you differentiate with respect to ML, I get CL minus lambda VL over ML squared. And from this you see immediately that ML has to be proportional to the square root of VL over CL. Lambda is just a scalar quantity, and then you can fix the lambda by enforcing the various constraints. That's how you get this constant in front. So if we use this optimal allocation, then I can plug this formula here, there, and see what is the overall cost of this estimator, if in the case we use the optimal allocation. Okay. Well, first, of course, this was optimization on real values. In practice, I have to take the closest integer. I cannot work with the real L, so I put the ceiling there. And then I plug this into the expression of the cost. So the overall cost, there is a sum missing, sorry, sum over L missing there. So if this ML times CL, now I can, ML is this ceiling operation, so I can upper bound by 1 plus the quantity itself. Okay, so if I look at this part here, you see that here I have a square root of CL, here I have CL, so when I multiply I get square root of CL VL, and then a sum over L, which means I get this sum squared. So the first term gives this sum squared multiplied by 12 to the minus 2. And then there is some extra term because of this 1. So we need to enforce that we run at least one simulation on each level. So we have this upper bound here on the cost. But often this term is negligible and we can just focus on this part here. Okay, so that's the overall cost. Maybe I change the order of the slides. Let's go straight to the. I come back to the slide later. So let's see at the end what is the overall complexity of this estimator. And this result is the main contributor is Mike Giles, who really popularized the method in this seminal paper in 2008, where he gave the first complexity result that was focused on stochastic differential equations, essentially. And then it was generalized as sliding proof, and the other seminal paper also with Rob and Adit and Cliff, more addressed to random PDs in the 2011 paper. Okay, so let's make again similar assumptions that I did for Monte Carlo. So let's assume that if we look at the expected value of how the expected value of QL converges to the expected value of Q in the suitable Z norm, this scales like HL to the power alpha, so the mesh size to some power alpha. But now in this mean square error analysis, there is also this other constant that appears, this variance of the differences. So I also have to understand how this variance of the difference scales with H, because that will be crucial. Okay, so let's suppose okay, the variance of the differences should not be too different than the variance of Q minus QL, so the exact Q minus QL. So let's suppose that in L2 sense, the error between Q and QL measured in the Z norm and the mean square sense, this scales like some HL to some other power beta. Okay? Now, this is a squared error, so one would expect beta to be 2 alpha, but it might be smaller than that because of this argument I mentioned for stochastic differential equations. The rate might be different if you measure in mean square sense or if you measure in law. So the weak error may be different than the strong error. One usually have, I mean, what is sure is that alpha is at least beta over 2, but could be larger than beta over 2 if you have a difference between weak error and strong error. So we make some assumption on the strong error, this L2 error. And then we have some assumption on the cost, that the cost increases when we refine the mesh and scales like HL to some minus gamma, HL to the minus D to the power gamma, number of degrees of freedom to some power gamma. So what we need in the mean square error analysis is actually bound on VL. VL was the expected value, was the variance of the difference. But this variance of the difference can be upper bounded by this term here, actually. And that's again a simple calculation, so the variance of the difference, I can write it as the expected value of the difference square minus the difference of the expected value square. I can drop this term. I mean, this term is of the same order of this one or higher. In any case, has a negative sign. So I can just forget about this and look at this, and then I can sum and subtract the exact Q. And use just triangular inequality, so you can upper bound this by Q minus QL and Q minus QL minus 1, and then they both decay proportional to HL to some power. And if I use geometric meshes, so geometric sequence, I can both upper bound up to constants this quantity by HL to the power beta. Okay, just because HL minus 1 is related to HL, so constant. So I can upper bound everything by HL to the beta. So essentially, if I make these answers on this squared error, this also gives an upper bound on the variance of the difference. Okay, so under these assumptions, this I have already said that alpha is always larger or equal than beta over 2 because of this weak error being always larger or equal than the strong error. And so here is the complexity result, and I will spend a few minutes to guide you through this result. So again, if we want to achieve a mean square error that is of order tau square, the cost, so the amount of time or resources that we have to invest to meet this tolerance scales in this way. And there are actually 3 different cases that may appear depending on whether beta is larger or smaller than D times gamma. Beta being this rate here, is the rate of this strong squared error, which is also the rate of these variances. Okay. And D gamma is the rate at which the cost is growing with respect to the mesh size. So essentially, comparing beta with D gamma, it means to compare how fast the variance decay versus how fast the cost increases. So beta larger than gamma, that means the variance decays faster than the increase of the cost, and beta smaller than gamma is the other way So in the good case is beta larger than gamma d. So variance is the decay fast over the hierarchy, faster than the increase of the cost. And in this case, the overall complexity scales like this is up to constants. It will be interesting to go deeper into that. What is in the constant, but it will not. So in this good case, everything scales like 10 to the minus 2. Okay, Monte Carlo rate. Monte Carlo rate, remember what was the complexity of the pure Monte Carlo? It's written here. In the pure Monte Carlo, we had minus 2 minus d gamma over alpha, and the d gamma over alpha was the complexity of running a solution on the finest discretization level. Okay? So what this result says, and it might look quite surprising, you drop this term here, so solving your PDE becomes of unit cost. Okay? Which looks striking, but what essentially this result says is that the cost is dominated by the Monte Carlo part. But if you want to kill the Monte Carlo error, essentially you have to run almost all the simulations on the coarse level. So the cost that you see here is the one of the coarse level and not the one of the fine level. The one of the fine level increases if you decrease the tolerance because you have to refine more and more. But the cost of the coarse level, if you keep the coarse level fixed, that's the constant. Okay? So that's somehow the optimal case, the one that you would like to have all the times. There is an intermediate case where those two contributions are balanced, and this gives some log factors on top. So it's 10 to the minus 2 up to log factors. And there is also the less favorable case, which is this one. So when the decay of the variance is not that fast over the levels, it's slower than the increase in the cost. In which case you don't achieve the 10 to the minus 2, you get the worse complexity. But you can easily check that this exponent here is always smaller than this one. You see, because you have minus 2 minus d gamma over alpha, which is this one, plus this beta over alpha. Okay? So even in this less favorable case, this complexity is still better and often much better than this one. So essentially you gain all the times if you exploit this hierarchy of discretizations with respect to the complexity of Monte Carlo. Now, this is a strong statement, of course, because all this is somehow an asymptotic analysis, assuming that you do have this decay, this nice convergence rates. You all know that if you have a complex CFD problem and you run it on a very coarse mesh and then you start refining, at the beginning you don't see any grid convergence, and you have to refine quite a lot to start seeing a nice grid convergence. So what I'm saying here is true if you are in this asymptotic regime where you see this nice grid convergence. Okay? Otherwise, if you use two coarse levels for which you don't have improvement in accuracy when you refine, it's actually questionable whether you should add them in the multi-level construction, because they might actually inflate the variance instead of reducing the variance. And then actually we come back on this point. One more comment on this last case. I said that alpha is always larger or equal than beta over 2. Okay, alpha is this weak rate and beta over 2 is this strong rate. In many cases, you actually don't see a difference between the weak and the strong. If you do some stochastic differential equations, depending on the scheme that you use, you might have, for instance, if you use the Milstein scheme, you will have the same weak and strong error. If you do this random PDEs, even let's say this elliptic model with a random field as a diffusion coefficient, even if the random field is quite rough. In general, you don't see this difference between the weak rate and the strong rate. So in the PDE constant context, we usually have this equality here. So this difference in the rates comes from somehow cancellations in the noise when you take the expectation. So in the strong rate, you are really following the two trajectories with that are wiggling around. But if you just compare the expectation, you might have some cancellation on this rough path that makes eventually the weak rate to be higher than the strong rate. But this cancellation doesn't always happen. So if we are in this case alpha equal beta over 2, and we look at this complexity here, this is told to the minus 2 minus d gamma over alpha plus beta over alpha, but beta over alpha is 2, so this cancels this one. So we get told to the minus d gamma over alpha. What does it mean? Again, compared with Monte Carlo, now it's the minus 2 that has disappeared. What does it mean? Essentially, it means the complexity now is all dictated by solving the PDE accurately, and you don't see anymore the Monte Carlo. So essentially, the Monte Carlo, the uncertainty analysis comes almost for free. Okay? So you don't have this total to the minus 2 bad effect of the Monte Carlo. Not as it is not there, but is just a constant in front. So I'm not saying that doing the whole multi-level Monte Carlo analysis costs exactly as solving one single PDE. This will not be true, but it will be just a constant factor of it. So like 100 times more, but this factor 100 times doesn't grow if you ask for a more and more accurate solution. Okay? So at least in this case here, you have essentially that this rate is the minimum between 2 and d gamma over alpha. So either sorry, I cannot say this. Not the maximum. The worst of these two rates instead of the sum of the two. Okay, that's essentially the gain that you have when you do this multi-level construction, and that's a much broader conclusion in general when you do any sort of type of sparse approximations, which I will briefly discuss tomorrow. So when you do this sparse construction where you have two somehow competing, two parameters, so h and m, but could be also two different discretizations. Instead of running all your simulation with the highest level in both, you try to sparsify. So if you go high in one parameter, you go low in the other, and you try to combine in some optimal way. So that's what I call a sort of sparsification or a multi-level construction. You hope for going from this complexity where you see the product of the terms to this one where you see actually the worst rate between the two. Okay, right, so here is the proof of this theorem here. Nothing really deep, is just to check the three different cases. So if we want to achieve a mean square error of order tau square, first thing that we have to do is to make sure that the bias is of order tau square. So we have to choose the maximum refinement level L so that we meet this bias constraint. Means that L should scale like tau delta is the geometric refinement. So I shown this geometric refinement at rate delta, smaller than 1. So then L should scale like log delta tall to the 1 over alpha. And then you look at the cost, which has this expression if you use this optimal allocation. So this optimal formula for M, plus this term here that makes sure that you run at least one simulation per level. Now, if we forget about this term, which is usually negligible, I can replace the ansatz for CL and VL. So VL grows like HL to the beta, so it means delta to the power L beta. And the cost, so VL decays as delta to the beta L, and the cost increases as HL to the minus d gamma, so it means delta to the minus L d gamma, and then everything is under square root, so I have to divide it by 2 here. Okay, and then I have to sum over the levels. Which I think there is a typo, should start from 0, the sum. And now you see where this distinction in the theorem comes from, because either this term is positive or is negative. If this is positive, this is a converging series. So even if I go to L infinity, it is just a constant. Whereas if it is negative, it blows up. Okay? And then if it is negative, essentially the whole sum is dictated by the last term. This is a geometric sequence. So the sum up to L is essentially proportional to the last term. So then we have these 3 cases. If beta is larger than the gamma, that's the case where this exponent is positive. Then I can sum up to infinity. It gives just a constant, and the whole complexity is tall to the minus 2. In the intermediate case, this is exactly 0. And then when I sum over the level, I get a factor L squared. But L is proportional to some logarithm of the tolerance. So that's where I get this tall to the minus 2 log tall squared. And in the bad case, this sum is controlled by the last term, which is delta to the capital L beta minus the gamma. And then I can replace the expression for L and gives this final expression. Okay? Yes, we just have to make sure in this theorem that this term here is actually negligible with respect to this part, which is the assumption in the theorem that 2 alpha is larger or equal than the minimum between beta and gamma. This assumption guarantees that this extra term is negligible. So you only get these 3 cases. Okay, so that's essentially the main result about the complexity, which says what you could gain, at least asymptotically, by doing this multi-level construction with respect to the simple Monte Carlo estimator. Let me come back to the slide that I skipped, which again is on this asymptotic regime. So what if we are not in the asymptotic regime? Should we include a level or not? I propose here just the check for the first level, but this somehow applies also to the subsequent levels. So suppose you just do a 2-level method, and you have just level 0 and level 1. And now you may ask, should I do my Monte Carlo level 1, or should I do the multi-level using both level 0 and level 1? Is it always profitable to do the multi-level construction, or maybe not? So you can check quite easily. So let's say, so if I do the multi-level, again, the comparison is in terms of cost for a given tolerance. Okay, we have a target tolerance tau. So is the cost of the multi-level smaller than the cost of the single level, question mark. So let's see what comes out. So if I do the multi-level, I know that I have to choose, and I do optimal allocation, I know that I have to choose M0 proportional to square root of V0 over C0 times this constant here, tau to the minus 2, and similar for M1. If I do the single level on level 1, okay, I have to choose M, so level 1, the variance I have the variance of the quantity Q1 divided by m that should be of order tau square. So I know that I have to choose m of the order tau to the minus 2 times the variance of Q1. But the variance of Q1, this is not a difference. So the variance of Q1 is not too different than the variance of Q0, because we expect that the variance of the quantity is more or less the same over all the discretization. So this is roughly tau to the minus 2 times V0, not V1. Even though we solve in V1, the variance, we don't expect that changes too much between level 0 and level 1. So what I call V1 is the variance of the difference. But here I don't have a difference. I just have the variance of the quantity itself. So M is roughly tau to the minus 2 V0, whereas the cost in Monte Carlo is the cost evaluating Q1, whereas the cost on level 1, C1, is the cost of evaluating a difference, Q1 minus Q0. Well, again, we could say this is not, the difference is not too strong. We could say solving the problem on level 0 has somehow a negligible cost with respect to solving the problem on level 1. So we can say that in this Monte Carlo here, computing a single realization of Q1 has a cost more or less equal than computing the difference Q1 minus Q0. Okay? So just to simplify the analysis, say the cost of Q1 is roughly the same cost as Q1 minus Q0, which is C1. So now we can compare the two costs. So in the multi-level, the cost is this tau to the minus 2 times the sum of the square root of V0 C0 plus V1 C1 squared. Whereas in Monte Carlo, the cost is tau to the minus 2 times the variance, which is said is roughly V0, which is comparable to V0, times the cost, which is comparable to C1. Okay? Good. So now we see that this quantity here is surely larger than this one squared. So that's larger than total minus 2 V1 C1. And if V1 is larger than V0, this cost is surely larger than this one. So this says that if V1 is larger than V0, you don't have any interest in using multi-level constructions. So the multi-level will only bring an extra cost without any benefit. Okay, so then I put V0 is the variance of Q0, and V1 is the variance of the first difference. So you expect that the difference Q1 minus Q0 is smaller than the quantity Q0 itself. But it's not always the case, because if you don't have any grid convergence here, what you compute of Q1 is somehow unrelated to Q0. So this difference might be of the same order of Q0. Okay. And if this is the case, you don't have any interest in including the level V0. You should start at least from level V1, and then you can repeat the analysis and check whether the difference between Q2 minus Q1 is smaller. So it means that if you try to plot the variances here, the VL versus the level L, if you observe the behavior of this type, so first an increase or maybe a plateau and then start decreasing, this part is useless. Actually, it just brings extra cost. You start benefit of the multi-level from here. Okay. So this somehow sets an rule and a guideline on how to choose the coarsest level discretization to start benefiting of this multi-level construction. Any questions so far? Okay. I think I went through these comments already. So all this analysis was done on the assumption of geometric sequences of meshes. Actually, one can do a refinement analysis if the sequence is not geometric, or trying to find an optimal sequence of refinements. But actually, this doesn't bring much in the complexity of the algorithms. So in this paper, we show that somehow these geometric sequences are nearly optimal. So we can stick to these geometric sequences. You get almost as much as you can get from the multi-level construction. Again, the two examples that I showed earlier for the Monte Carlo. So if you take this SD example, again, we discretize with order Maruyama. The weak error is order 1, the strong error is order 1/2, which means that if we look at the variances, they are essentially of the same order of the error squared, which means they are also order 1. Okay, so the beta here is 1, and the alpha is 1. So alpha is actually twice over 2. So alpha 1, beta 1, d1, gamma 1. And then we are exactly in the case where beta is equal to d times gamma. So we get this log tau to the minus 2 up to some log terms. Okay, we're almost in the best case, compared to the Monte Carlo, which was tau to the minus 3. So it's quite a substantial improvement. So if you want to get one more digit of accuracy, the cost increases by 100 instead of 1,000, 100 up to some log terms. You can remove the log terms if you go to a better scheme that has a better beta. For instance, the Milstein scheme. The Milstein scheme is a scheme that has alpha equal 1 and beta equal 2. So the strong rate is equal to the weak rate. The problem of the Milstein is that it's not always implementable, easily implementable. So it depends on the structure of the noise that you have. So in some cases it's not a practical scheme. But if you can implement it, then you have beta equal 2. It means that now you are in the good case. So you're fully in the good case, and you can remove even these log terms. Let me just mention this nice paper by Joyce and Sprug, where they show that even in the cases where the Milstein scheme is not implementable, if you use it within the multi-level construction, essentially the Milstein scheme is based on a Taylor approximation, or an Ito-Taylor approximation of the SDE. So you do some expansion, and then you have to evaluate a bunch of terms involving the noise. Some of those terms can be easily simulated. Some others cannot. So they involve some multiple integrals of the Wiener process, for which you can characterize exactly the distribution and can come up with an easy way of sampling those random variables. If you just forget those bad terms that you cannot evaluate, but if you do it within a multi-level scheme, essentially things work out nicely, and you recover the optimal complexity. And much of the case constituting that there is this idea of antithetical Milstein that can be used inside the multi-level Monte Carlo to recover this optimal scaling, even in cases where the standard Milstein is not easily usable. Example with a PDE. with random coefficients. Again, okay, here I don't know why I consider the nicer case where the error in the quantity of interest scales like h squared, so you profit of some regularity of the quantity of interest, so the cost grows like h to the minus d times gamma. So okay, in this setting, if we look at the 2D case, we have alpha equal to 2, beta okay. Again, I said in the PD setting, you usually don't have this distinction between weak rate and strong rate. So the beta is 2 alpha. So beta is equal to 4, b equal to gamma 1. So you are in the good case. And then in this good case, no, you are in the yes, the good case. So here you get tau to the minus 2. Whereas the pure Monte Carlo is tau to the minus 4, so even a more dramatic gain. And if you go to a 3D problem, same setting is even better, so this stays tau to the minus 2, whereas this was tau to the minus 5. Okay, so in the PD setting, the gain with multi-level is even more pronounced. Okay. I'd like to discuss some more practical aspects on the implementation. So in practice, what we have, so what I showed as more theoretical analysis, assuming that you have those rates and you can construct this optimal allocation, then this is what you should expect in terms of asymptotic complexity. Now, can we achieve this in practice? Well, if you want to achieve this in practice, you do have to calibrate the multi-level estimator in the right way, so that it matches this optimal allocation and eventually this asymptotic complexity. And calibrating the estimator means first equilibrating the bias error and the variance, the statistical error, because if you are very unbiased, you might not observe this improved complexity. And for the variance part, you have to do this optimal allocation. This optimal allocation, remember that the sample size scales like the square root of VL over CL. It means that you have to have some estimates for the VL and the CL to do the optimal allocation. It means that within the simulation, you have to estimate a certain number of terms to be able to do the optimal calibration of the multi-level estimator. So again, for the bias, if you want to achieve a given target tolerance, for the bias you have to choose the finest refinement level. And again, here you can either use some posteriori estimators, or as I mentioned in the previous lecture, since you are, in any case, you are solving problems on a sequence or refined mesh, you can also often just use a simple extrapolation to come up with a reasonable bound for this bias term. For the variance, and in particular the optimal allocation, you need an estimate of these variance terms, so which is the variance of this difference, so same quantity computed on 2 consecutive grids. And again, typically you would use a sample variance estimator, so you run a bunch of simulations on these coupled levels. You estimate the variance, and then you plug it in this formula, and then you can also estimate the cost, the runtime cost of doing this simulation. And then with those estimators, you can use the optimal allocation formula. Okay? Yeah, so you do some simulations to figure out what is the bias, and this sets the finest level. Now, one crucial point here is that to estimate these parameters, you need to do some simulations. Either you use completely a priori information, but then the constants might be completely off, or you try really to do it a posteriori, so try to estimate from the simulation itself, but then you have to run some simulations to estimate this variance. The number cannot be too small, you cannot just run 2 simulations here because the variance estimation will be too unstable. But this does pose some problems because somehow in the whole multi-level construction, you really would like to, in the good case, beta larger than d gamma, you really would like to run only 1, 2, 3 simulations on the finest level that will cost you 1. But then this estimation, this error estimation, might end up being much more costly than running the whole simulation, the whole multi-level Monte Carlo estimator. So one has to be a little bit careful. There are a couple of ideas to adapt the algorithm. So this is the algorithm that is proposed, that is, you can find it in Mike Childs. So I mentioned the seminal work by Mike Childs from 2008. Then he also wrote an Acta Numerica that gives an overview of multi-level Monte Carlo. So I invite you to read. It's a nice review article to read on multi-level methods from 2015. So in there you have also an adaptive multi-level Monte Carlo algorithm, which essentially adapts both L and M, so the sample sizes. So you start running simulations on certain levels, and then for each level you estimate the variance, and you use this optimal formula, and you decide if you need more simulations on that level. And then, given all the simulation that you have done, you estimate the bias, and if the bias is above the tolerance, you add a new refinement level to the whole construction, and you keep on going. But when you add a new level, you have to run a minimum number of simulations on that level to have an estimate of the variance on that level. Okay. So as I said, this estimation of the variance might actually spoil the complexity result because it ends up being more costly than the whole multi-level. So in this other paper here, we propose another version, we call the continuation version, where somehow we try to extrapolate information. So we target a sequence of tolerances. So the final one is the one you want to achieve, but you start building a Monte Carlo estimator, multi-level Monte Carlo estimator for a larger tolerance, and you collect information. With this information, you try to fit these decay rates of the mean and the variances. And then when you go to the next tolerance, you will have to add a few more levels, and those few more levels you just extrapolate the rates that you have fitted on the previous level. So you don't run simulations on the new level, just to extrapolate from the knowledge that you have from the previous level. So essentially, over this algorithm, you improve the fit of these rates, alpha, beta, and gamma. Every time you have more information, and then you can achieve a better fitting. And then you can use this on the new level, whereas on the levels which you have already visited, on which you have many simulations, you can use the actual sample variance there instead of the model. Okay? And you can also come up with fancy ways of doing a nice blending between the sample variance and the model. So if you have very few simulations, you use more the model. If you have many simulations, you use more the sample variance. So we came up with a sort of Bayesian update of this information to do this blending. Okay, a couple of more comments. I've discussed the splitting of the error equally between bias and variance. Of course, this is also not needed. You can think of different splittings between the two. And you can also use some central limit theorems that are available from the multilevel Monte Carlo. This is one reference. There are others that show the central limit theorem for the MMC standard. So if you use the central limit theorem, you have a probabilistic bound on the error that has a bias part and the standard deviation part. And then you can decide to split unevenly the two. So you allocate 1/θ fraction of the tolerance to the bias and θ fraction of the tolerance to the variance. And you can also figure out this optimal allocation within the overall algorithm. In a sense, you decide on which level you have to add to meet the next tolerance. But now once you add this level, maybe this bias reduces by substantially. It means that you have more space to more error that you can put to the variance, and if you do this optimal allocation, you can actually gain quite a bit on the overall performance of the model. So this is just some examples to show that it does indeed work quite. I mean, this algorithm that learns the rate and automatically improves the construction does actually provide does a good job. So here, this is a target tolerance. This problem was a 3D elliptic PD with some gamma coefficient and P1 finite elements. So we are in this setting alpha 2, beta 4, gamma 1. If we use an iterative solver, so the gamma was fitted. So gamma 1 with an iterative solver and gamma 1.5 using a sparse direct solver. So here we repeated 100 times the simulation with MLMC, with this adaptive MLMC algorithm, and we plot for different tolerances the actual error. We have the reference solution, so we can compute the actual error, and we see that I mean, we are putting a confidence of 95% and only few runs, actually less than 5 runs over 100 are above the tolerance. So this algorithm, self-learning algorithm, does meet actually the required tolerance, both in the iterative and the direct solver. And we do actually recover the theoretical convergence rates with this adaptive algorithm that is predicted by the theory. Of course, only asymptotically, so you see that pre-asymptotically you might be a little bit off the complexity, but if you start reducing progressively the tolerance, then you go on top of the predicted complexity in the direct end. So the iterative one is a good case, Tottenham's 2. The direct one, because of this increased gamma, is in the worse, less favorable case, because it's like worse complexity, and in both cases we meet the target. Okay, let's keep this slide here. So we also applied this to some more challenging problems that so we quite old papers with my former PhD student Michele Pizzaroni on CFD computations. So those are compressible Euler equation. In this example, we also did some compressible steady runs simulations. So this is an airfoil, and we are looking at the flow around the airfoil and computing some quantities of interest that are the pressure coefficient of the lift on the airfoil, playing with some uncertainty in the system that could come either from operational conditions, so the angle of attack that could vary over the flight, the Mach number, the pressure and temperature at infinity, or some geometrical uncertainties on the shape of the airfoil, some manufacturing uncertainties on the shape of the airfoil. So all these geometric parameters that describe the shape. So we used a sequence of meshes. Those were constructed ad hoc somehow, trying to refine where you expect this presence of attack shocks. So the shock is So around this region, depending on the value of the parameters, we refine the mesh here in this region.
Sorry, can you just go back one slide? I'm in a certain column. What does TN mean?
It's a truncated normal. So engineers like normal, but then I at least pretend that they truncate not to have negative values.
We model each with two quantities.
Yes, so where does this uncertainty models just come from? There was no real data used here to fit this distribution, so it was just reasonable bounds on the uncertainty of those parameters. So that's the sequence of meshes, and you have here the number of cells. So this was solved with finite volumes. So it's the number of cells in the different levels, and that's the pressure distribution over the airfoil. So here you are spanning the lower edge and the upper edge of the airfoil over the axial coordinates. So this is the lower edge, and this is the pressure on the upper edge. And of course, you have much bigger uncertainty on the upper edge because of the presence of this shock. And the position of the shock changes with the parameters, so this gives this big band of uncertainty. So this is the mean plus some 2 or 3 standard deviation from this MNMC analysis. This is a little bit of history of the multi-level adaptive algorithm, multi-level Monte Carlo algorithm. So we start with only the first 3 meshes, running 20 simulations on each mesh, and we start collecting information on those 3 meshes, and then the algorithm starts adapting and choosing automatically the number of simulations to run on each level to meet in sequence the different tolerances until the last one. Again, it's continuation algorithm, is self-learning by enriching progressively and going to smaller and smaller tolerances. So this is the final run, which you see uses about 4,000 simulations on the coarsest mesh. The coarsest mesh have 5,000 cells, so it's relatively cheap, and it runs 5 because it was set as the minimum. We could even lower this one. We could even go to 2 or 3 simulations on the finest grid. Okay, and you see this nice geometric decay of the sample sizes over the levels. This is the beta fitted, so it's actually beta equal 2, which is not too bad with this type of simulations. And this is a result, the complexity result between the multi-level and the single level. So if we run all the simulation on the finest level, again, by calibrating correctly for a given tolerance, we figure out what was the right level to use to have a bias of that order, and then we computed the right sample size to meet the tolerance. So this is the Monte Carlo line, and this is what is provided by this adaptive multi-level Monte Carlo. You see that we're always below, and the gain could be quite substantial if you go to more tolerances. This is also one thing to keep in mind with the multi-level construction. You really benefit when you go to accurate solutions, which is what is usually very difficult with Monte Carlo. So getting accurate solutions with Monte Carlo is almost impossible because it's just too expensive. If you're shooting for a very crude solution, so 10% accuracy, it's not so obvious that you really gain by multi-level Monte Carlo. Okay, sometimes Monte Carlo is actually, because it doesn't have this overhead of running simulations on the coarser level, so if you just shoot for very crude tolerances, maybe pure Monte Carlo is just okay. So that left was for the lift coefficient, so a scalar output. The right one is for the pressure distribution over the airfoil, so the whole distribution here. And things are slightly worse because the beta now is much worse. So the point is, if you look at the actual pressure distribution, there is this shock wave that changes position depending on the parameters. So when you look at the error, this is a sort of strong error, so pointwise polarization. You might have that on the coarser level, on the finer level, the shock in a slightly different position, and then if you measure the error in, let's say, an L1, you get a very poor convergence rate, strong convergence rate. That's the 0.9 that we fit. Whereas if you just integrate over the surface, somehow you average with respect to the position of the shock, so the lift actually converges much nicer as a quantity of interest. So the lift has a decay rate θ equal 2, which is nice, whereas if you do a pointwise comparison of the pressure on every point of the airfoil, because of this presence of the shock, it converges very poorly. And this does imply that multilevel Monte Carlo multilevel Monte Carlo struggles a bit more. You see that on the finest level we have to increase, we cannot just keep a minimum number of samples, we have to actually increase quite a lot the number of simulations on the finest level to meet the tolerance. So this decay of the sample size is less dramatic than that one. But still, in terms of complexity, we do improve with respect to the pure Monte Carlo. Okay?
Sorry, a question on the last slide. What does this deterministic line represent on this?
This is just the cost of one solve.
Okay.
So a pure deterministic solver, one simulation to meet a certain tolerance.
Oh, okay. I see.
So that's the reference size. So this shows how more costly is your uncertainty quantification with respect to just running the deterministic solutions. So it's at least 3 or 4 orders of magnitude more costly to do the whole vacuum analysis. And here we are in this case of epsilon to the -2. If we were in this other case, the blue line would be parallel to the red line, just shifted up. And in this case, it's even steeper because it's dominated by the Monte Carlo, not by the solver. So here again, robustness analysis. We repeated many times the whole adaptive algorithm just to check that every time we more or less get the same sample sizes over the levels. So variability is relative. Of course, there is variability every time you run, you get a different sample size per level, but overall it's relatively stable and it always gives a solution within the accuracy that we have requested. There are some parameters here that it has to choose in the algorithm because of this blending between the sample variance and the model. So there are 2 parameters to set, but even setting quite different values for those parameters, so the algorithm seems to be quite robust. Okay. Okay, maybe I conclude with this comment. So what I've discussed in the multi-level algorithm was to do independent samples between the levels, so you approximate the difference over the level completely independently from one level to another. One might wonder if this is really needed. So you could think of a subsampling strategy. So you run, I don't know, 1,000 simulations on the coarse level, and then you select 500 of those, and for those you solve on the first level, and you compute this difference, and then out of those you select 200 for which you go to the second level, and so on. This creates correlation between the estimators among the levels. So it does complicate the analysis, because now I cannot exploit this independence anymore, which makes this very simple formula for the mean square error. So from the point of view of the analysis, it's nicer if you work with this completely independent one. But it can still be analyzed also from the theoretical point of view, this strategy, just by using triangular inequality. Of course, that's not optimal, so you pay something. So this would be the estimator. So I run a certain number of simulations on the finest level and I compute this difference. Then I go to the previous level and I keep already the simulation that I had here. And for those I compute also the previous level, and then I add a few more to have a better estimate there, and then we keep on in this way. So now the mean square error of the estimator, we can split the bias and variance, but now you cannot easily pull out this sum out of the norm because you lack independence. So now you're obliged to use a triangular inequality here. A triangular inequality brings a factor L in front. And then you have the sum of this, but now within each level you use independent samples. So here you can pull out a 1 over m factor. So here everything decouples once you're here. So then you get again this nice formula VL over ml. But you have paid this capital L in front. So in terms of complexity, the capital L scales like log tol. It means that essentially the whole complexity, if I go back to the complexity result, if you reuse samples between the levels, essentially this result, essentially this result worsens because you have a log tol in front. Okay. But this is from the theoretical perspective, you pay a log toll. From the practical perspective, you might not see the log toll and you spare some computation. Although in general, the gain in computational time is not that big. And also it's more difficult then to do error estimation because again, you have this correlation between the level. So it's a little bit debatable whether it's better to run completely independent simulations or try to spare simulations from one level to another. Okay, that's a good point to stop. If you have questions, I can answer now or later. Yes.
I have a question about the case of oscillatory coefficients. So naively, I would expect that the course's grid needs to resolve these coefficients. Are there some tricks which you can play, for example, like cutting the KL expansion to the level somehow to somehow avoid that?
Absolutely. So again, the somehow key point one has to be careful with is this keeping this telescopic structure here. If you don't, you have to be very, very careful on what you do. But what is Q0 a priori is arbitrary, so you could say discretization is 0, but at the same time I throw away a few KL modes. As long as you are consistent here and here, so you do exactly the same approximation here and here, that's fine, because this term simplifies it. So it means that when you do this difference, here you will have more, you will use more KL modes than this one. So this is on a refined mesh with more KL modes. And you compare with the one on this coarser with fewer KL modes.
Yeah, I see.
The question is whether the variance is still small. You have to estimate
exactly how to get triangle inequality to estimate the different KL solutions and the different approximations. Yes. And then
somehow the number of terms that you throw away should be somehow comparable with the discretization error.
Yeah.
Then you can also think of multi-scale problems where you have really fine structures, and then you could say, okay, here I could use a multi-scale solver here, and here I go to a full-scale solver. You can also, so what do you use as a course is a part of the game, of the design process. what is a good course model.
Thank you.
Yes.
One question about the Banach valued case. So you told us that if our output space has this Rademacher type, then we have this generalized Marcinkiewicz segment inequality, and then we can derive analogous results as in the Hilbert valued case. Does the reverse statement also hold? So if we have this generalized inequality, then our Banach space is of some Rademacher type, or are there some topological examples where we have this inequality, but we have not this Rademacher type?
Okay, I would have to check this, but I believe yes, but it is. If your space is a Rademacher type not equal to 2 is a Banach space, it cannot be a Hilbert space.
So can you say?
If your space has a Rademacher type P is strictly less than 2, it cannot be a Hilbert space. Was this your?
Yeah, but so does there are there cases where we have no Rademacher type but still this Marcinkiewicz segment inequality?
This no Rademacher type means Rademacher type P equal 1 essentially wouldn't give any decay, but no, wait, so you say if you have a Marcinkiewicz inequality,
Basically, I'm wondering if the reverse statement of this proposition holds. So, does if this segment inequality holds, does it also imply that we automatically have some Rademacher type? So we have a direct characterization between these two things, or?
It's a good question. I don't know.
Okay,
I have to think about everything.
So my question relating to the question like what happened if the Z not Hilbert, what I can do with multilevel Monte Carlo?
I mean, essentially, you can generalize the whole theory, but you will have to use this other type of constructions, and it's. I think I put a reference. So this paper here goes through the. Here is the focus is even on k moments, but it does include also the mean. So here they discuss how to do the multi-level construction in the Banach setting. Essentially, yes, everything goes through by using this other type of inequalities. Time for lunch, I guess.